Hello, here's some background on Alessandro Volta. So this is the Italian physicist and chemist who we probably first think of, at least in physics, as being the guy who's got the unit of electric potential named after him, the volt. He's also credited as being the inventor of the electric battery, which I'll get onto in a moment. He also discovered quite a few things in chemistry, including being the first person to isolate methane. So he discovered methane. As with many people back in the day who became scientists, he was born into an aristocratic family. That was how he got his education that could move him into the field of academia. And he was born into this aristocratic family in Como in northern Italy. So Como is just sort of north of Milan. And he spent most of his life really in northern Italy, whether in Como or at the University of Pavia, which is just south of Milan in northern Italy. And it was while he was a physics professor that he, in the 1770s, he made his sort of first real statement in physics. He popularized the electrophore. So electrophore, this is a device for sort of isolating some static electricity. So you get these two plates. You've got one dielectric plate. So if you remember with dielectrics, they're materials which they're insulators, but they can be polarized. So you can align molecules in them so that they're all lined, plus minus or minus plus, they're all lined up the same way. So we've got some dielectric plate and then we've got a metal plate. And we've got these two plates. So you start with the dielectric one and you polarize it. You align all of these molecules inside the plate by rubbing it. So you start off by rubbing that plate so that we've got negative on one side and positive on the other side. Then you get the metal plate and you put it close to this polarized dielectric plate. That pushes the electrons in the metal plate to the opposite side, to the far side of the metal plate. So that's actually moving the electrons. In dielectrics, you're not getting that movement, you're just getting this polarization. In the metal, you are getting the electrons to actually move to one side. You can then earth that side of the plate. So all these electrons are then removed from the plate. That then leaves you with a positively charged metal plate, which, you've then got a static source of electricity. So that was what the electrophore was designed to do, and Volta made good use of this. These were the early days of looking into electricity and magnetism and such like. So having a way of generating a charged plate to actually create one of those was particularly useful in the lab. So he did that in the 1770s. It was also in 1778 was when he isolated methane. He had been reading Benjamin Franklin's work on flammable air, as Franklin called it, and Volta followed up Franklin's work, and he managed to isolate methane as being this flammable component in air. He also was studying what we now call capacitance. It was Volta who first observed that the charge stored on a capacitor is proportional to the potential difference between the plates of the capacitor. So we can see that's pretty much our Q equals CV equation that we use when we start looking at capacitance. But the main thing that he's remembered for is the invention of the electric battery, or the voltaic pile. So this was getting now to the 1780s, and it was following on from Luigi Galvani's work with the twitching frog legs. Now, you probably come across this. Galvani had this dead frog, and he was probing away, sort of jabbing at it with some electrodes, and he found that the frog's legs would start twitching. So you'd have two electrodes, frog leg, you'd jab these electrodes in, and then you'd get a contraction of the muscles in the frog leg. Now, Galvani thought that this was evidence of some kind of innate animating spirit, this sort of built-in electricity that animals had, that was a life-giving force that was inside animals. Now, Volta would say, well, no, this isn't what's going on. What's happening here is that because you've got two different metals in these electrodes and they're being poked into what is essentially an electrolyte, so a liquid with charged particles in, the two different metals are causing a flow of electricity. So this was Volta's conclusion, and he showed this by removing the frog from the experiment. He said, right, well, first of all, let's get rid of this frog and we'll replace it with some brine. So, salt water, essentially, very concentrated salt water. And he soaked porous paper in brine, and then he put two different metals on either side, so say zinc and copper, and then he showed that this then produced a potential difference. It produced a current because the ions in the brine were moving in different directions. Now he soon replaced the brine. He started using sulfuric acid, and he had zinc and copper. So he'd have a zinc plate, he'd have a copper plate, and he'd have sulfuric acid in between. So this is getting a little bit closer to what we'd recognise as being a battery nowadays, although we still don't use sulfuric acid, zinc and copper in them. But what he was showing with this, I suppose the way it works, he didn't know the ins and outs of all of this because the electron hadn't been discovered yet, but he was just looking at the experimental findings. Oh yeah, we're getting electricity out of this. But the sulfuric acid, our H2SO4, that's splitting into two protons and then a negative ion as well. So this is what we've got floating around between these plates. Now the zinc gets oxidized. The zinc actually gets used up, unlike the copper. But the zinc is, we're getting these zinc like 2+, these positive zinc ions are going into the sulfuric acid. They're sort of dissolving off from the zinc plate. That's leaving a couple of electrons behind on the plate. So you're getting a build up there of electrons. The hydrogen here, the protons, these protons are then pulling electrons off of the copper plate. So the copper isn't actually reacting, it's just acting as a catalyst. It's providing electrons, which then combine with these protons to produce some hydrogen gas. This hydrogen gas is then bubbling away. It ends up slowing down the effectiveness, reducing the effectiveness of the cell, because this hydrogen builds up around the copper plate, which makes it harder for the copper to actually provide more electrons because everything's getting blocked by these bubbles of hydrogen gas. But the overall effect is, you can see we're getting this build up of negative charge on the zinc plate and a build up of positive charge on the copper plate. So if you then connect this up, and we've now got ourselves a circuit where we've got movement of electrons as we're going from this difference in potential between the two plates. So you can actually replicate this. It's something that you can do to some degree just at home. You can get some porous card or porous paper, soak that in salt water, and then just stack up coins. If you alternate silver coins and copper coins with a bit of salt water soaked card in between them, then you can hook that up, get a wire, and you might be able to light up a small bulb or something like that. It's something that's possible to do. So that was the first step into setting up a voltaic pile. So a pile was as in you just keep on piling these things up, and you put more and more of them on, and you can work out what sort of potential differences are you going to get a greater potential difference with different combinations of metals. This is the sort of level of experimentation they would have been doing back then. because they didn't know the chemical process that was actually being carried out by all of this. They didn't know all of these equations, but they could, try different metals. They could try different electrolytes. They could put these voltaic piles together in different ways and then test which one is going to be creating the largest potential difference. It's not that hard to make these sort of qualitative comparisons between different voltaic piles. So yeah, that was the setup on those. He spent most of his life, as I say, up in there in northern Italy. When he retired after 40 years at the University of Pavia, he went back to Como in relative seclusion, and he lived to a ripe old age. I mean, he was in his 80s when he died after a very productive life. So yeah, guy well worth knowing about. And if you want to know more about cells, I'm doing a separate video on batteries, alkaline batteries, nickel, cadmium, lithium ion ones. So that goes into more detail of what's actually happening in cells nowadays, the ones that we're actually using, rather than this early day stuff that we don't really use these sort of materials and electrolytes anymore. So get a bit more up to date by looking at them in more detail elsewhere. But there you go, Alessandro Volta.